yeah, baby. I've got the best music, the best espresso, the best cream. Celebrating the best ideas. Oh yeah, baby, this is home. I'm glad you guys could join us. Today we're doing some more calculus. What we got to do today is we got to practice the Fantastic Four methods, the ones we learned last time, the rewrite, plug-in, engineers, and graphing. We got to practice those, and not just practice those, but we're in a really nice position to add a little something to our previous ideas. That's the name of the game today. First, I'll turn your attention to the old way we did things before, or the old. We've done dozens of these limits, but I want to turn your attention to this portion right here, right there. Specifically, that right there. All of our limits that we had before always went towards either infinity or negative infinity. Those are x's are going towards the ends that way. So they're horizontal asymptotes. Which is not the way this story is usually told, but I thought it was an incredibly instructive way to do it because it gets it's a very, very gentle and effective introduction to the limits. However, if you notice that after you make note of that all of our limits were going towards infinity, the next natural question is, could the limits have gone within the real number line, something inside between infinity and negative infinity? For example, could the limits have gone to x goes to 5 or x goes to 2? That sort of stuff we never ever did before in our class, and so that's why today we want to do a couple of things that are really, really important. We want to practice our really, really nice methods here, our 4 methods, and we want to add a little something. And the one little something that we want to add is we want to start looking at limits in the middle of on the real number line, not just at the ends, towards positive infinity or negative infinity. That's the name of the game today. So here it is. For example, have you ever wondered, what if you have some function f of x and x is going towards 2? I'll give you 2 scenarios, okay? 2 for the price of 1. First scenario, everything's nice. I introduced these balls now. You're going towards here are your x's. Your x's are somewhere here, and they're going towards 2. And so you got your ball here going towards 2, and then as you approach 2, your job is to look at the y, okay? Right here, look at the y. Which y is it approaching? Maybe this y. Let's add some values here just for fun. Maybe this y is 1, this one is 2, this one is 3, this one is 4. Maybe the y's go up like that. And so your job here, you got 2 eyes, right? Keep one eye on the ball as it goes towards 2, and keep the other eye on the y-axis and try to predict what's the best prediction for the y value as your ball gets closer and closer and closer to the 2. And you say, well, that's obvious. As the ball gets closer and closer to the 2, the limit is equal to 3. Now that, my friends, that's what happens on an ideal scenario. But these functions can be so much more complicated than the ideal scenario. I can't even begin to tell you how complicated these functions can be, or how unideal. And so to appreciate the definition of the limits here in the middle, we need to look at an unideal scenario, or less than ideal scenario. Suppose the function was a little wicked here. You got pieces over here and you got pieces over here. This is less than ideal, and so you try to predict what's the best value here. And let me see, you grab your ball here and you say, okay, well, let me see. So you grab your ball here and you say, okay, my x's, the ball is going to follow the x's, and the x's are going to go that way, but the ball is going to stay on the graph. So here I go. You see the ball's going on the graph? The ball's going on. Your eyes, you should have 2 eyes. One eye on the ball and the other eye on the y-axis, okay? On the y values. So I made this little yellow line so you could keep an eye on the y values. And so the ball is going and going. Where's it going? Is it stopping here? No, it's going all the way to 2. I need to get it closer and closer and closer to 2. And as I get it closer and closer to 2, you need to predict the y value. You need to predict the y value. You say, oh, the best prediction is 4.5. And then you say, okay, that's really good. The best prediction was 4.5. And you may say, well, wait a minute, I have some objections, and you should have some objections. What if you had gone to 2 from the other side? See, we had never ever encountered this problem before because all our limits were going towards, for example, infinity, and there's nothing on the other side of infinity to come back from the other side. It was all of these one-sided limits, because there's all the positive infinity only has one side to go to it from the left. Negative infinity only has one side to go to it from the right. So we never had this issue of something in the middle where you could approach it both ways, and you try to make, you have to predict now the best prediction, but now you got two of them. You got the left and the right. And here's the objection. If you go from the left here, again, my x's are going closer and closer and closer and closer to the 2. And meanwhile, as I move my ball, your job is to keep two eyes here, paying attention. One on the ball and the other eye on the y-axis as it moves, 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 as it moves. And then it's getting close to, say, I don't know, let's just call it 3 for fun. You say, wait a minute, whoever got this one, they got it wrong. They're probably beginners. Maybe they're watching some other lectures from some other guy. I don't know. So the real limit should be 3. The limit is 3. Whoa. And the other guy says, no, you're the one that's Which one is correct? Which is the correct limit? Should it be this one that's approaching, the best prediction is 3, but from the other side, the best prediction is 4.5. Which one wins? This is the problem. And so that gives rise to a new notion, the notion of two-sided limit. And so we actually separate the two issues and we say, you know what? These ones right here, where whoa. Move for me, please. Let me see. Keep your eye on the ball here. So we actually have to give rise to new notions here. The notion of a left limit or a right limit. If it's a left limit, then it comes from the left. And so this would be x's approaching to from the left. And here it is, the ball. Keep your eye on the ball as you approach. Okay. So this is correct. Everybody, no matter which lecture you're watching, everybody should agree that the left limit is equal to 3. There's no controversy there. And a brand new concept for us, a left limit. Left and right. So similarly, you'd want to ask, well, what happens from the right? And so you'd say, okay, this time I'm going to take my x's and they're going to be coming towards 2 from the right. So it'll be maybe like 2.1, then maybe it'll be 2.01, maybe 2.0001. The x's are coming and coming and coming close. By the way, I'm giving you hints here on how to do the engineer's method as well. Over here, they'd be like 1.9, 1.999, etc., etc. Anyways, I digress. Let's keep your eye on the ball. Two eyes. One on the ball, one over here on the y, right here. One on the y, one on the ball. The ball's getting the x's are getting closer and closer and closer and closer to 2. Closer and closer and closer to 2. So, okay, the right limit, for sure, no matter which lecture you're watching, everybody should agree, the right limit is equal to 4.5, and that would be correct. This, my friends, this is the idea of two-sided limits. They occur everywhere. Let me see. The idea here is that we will say that the limit exists when we write things like this. The limit as x approaches 2 of f of x is equal to blah. We can only say that it's equal to something if when you come from the left and you come from the right, they actually match. If they match, then we say the limit exists, and we don't talk about the left or the right because they're both the same. But if they don't match, then we say the limit does not exist. In this case, the limit does not exist. Okay? There's no limit because the left and the right don't agree. However, there is a left limit and a right limit. I'll say there's a left limit, there's a right limit, but there's no two-sided limit. If it doesn't have a little plus here or a minus, like these ones, the implication is that they got to match from both sides. Got that? That's really important. Alright, so, and by the way, that will happen for everything that's, here's a number line, here's infinity, and here's negative infinity. These ones over here, they only have one-sided limits. They go from the, numbers keep growing towards infinity from the left. These ones, they only go from right. But everything in between, like 2 or 5 or negative 10, all these have two sides to them. So whenever you say that there's a limit exists in here with any real number, then it's got to exist from both sides. Alright, let's try this one. Let's try our graphing method. This is a famous graph. It's like a V shape. It's shift to the right a couple units. I think it looks kind of like this. So let's try it and see. X is going towards 2. Here's 2. And here, let's every time you check these, you got to check from both sides. So let's do one at a time. Let's check from the right. So you put the ball on the right hand side and you make your x's approach 2 from the right. Now your job is to keep 2 eyes open, one on the ball. Keep your eye on the ball and keep your other eye on the y. I'll slow down for you because actually it's so nice about tape, you can pause it. Going down, 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 down. You got to predict the y value as the x's get closer and closer to 2. What is your best prediction? If you say 7, I'm going to stop this, walk out of here right now. You can't say 7. You would say that the limit as x approaches 2 from the right for my function here is equal to 0. Because that is the best prediction. As I move from the right towards 2, the y value is going towards 0. And you'd be correct. And so we'd leave that ball there. And let's pick up another ball and start off from the left. Now I want my x's going to the right, to the right, to the right, to the right, approaching infinity close to 2. And I want to observe 2 eyes, one on the ball, one on the y. As I move closer and closer and closer and closer and closer and closer, look at the y. Where is it going towards? The y value, well, whatever. The y value is going towards 0, and so you would say that the left limit as x goes towards 2 from the left of the function is equal to 0. Now look at this. The limit is ever going to 0. The limit is ever going to 0. They match. See, they match. 0, 0. Therefore, the two-sided limit, the one that doesn't have a plus or minus, exists and is equal to 0. That's how you do two-sided limits. And everything in the middle is two-sided, unless it has a little plus or a minus up there. Clear? That easy or hard? Want to try another one? Oh, super famous. 1 over x squared. The graph looks like this. Let's go from the left. From the left, your best prediction is going towards infinity. From the right, your best prediction is going towards infinity. I'm not going to do the balls anymore. The balls are just for beginners. Well, sometimes I'll do the balls. But here, I'll do it again. This is going towards infinity. This one is going towards infinity. They match, and so we say the limit exists to 0 from both sides, the left and right, and they're equal. They're equal to infinity, and so we would say that this is equal to infinity. That limit is equal to infinity. Clear? Pretty easy, right? The graphing thing is really, really powerful. It's a good way to visualize things. Let's look at this one. As you move from the right, you're going towards positive infinity. This is x going towards 0 from the right. X going towards 0 from the left, that's bringing you down towards negative infinity. That's going down, that way. So from the right it's going to infinity, from the left it's going to negative infinity. That's not good. They don't match. They have to go to the same place, and then we have a limit. If they don't match, forget about it. There's no limit. Forget about it. So we would say the limit does not exist. Oh, I don't say it's equal. I say the limit does not exist. Okay. By the way, the right limit does exist. I could also add this, that the limit as x goes to 0 from the right. That's okay. That's clearly infinity. And the limit as x goes towards 0 from the left of 1 over x, that's clearly negative infinity. I do have a right limit and I do have a left limit. I just don't have a two-sided limit. Clear? Alright, let's see the next one. You guys want to use some balls? So from the left, from the right, you got to keep your eye on the ball. Let's say these are what units of 1? 1, 2, 3, 4. You got to keep your eye on the ball and keep your eye on the y. What is the best prediction for the y value? So, from the right, it's 4. So let's make a note of that. The limit as x approaches 5 from the right of f of x is equal to 4. And then let's go from the other side. Okay, from the right, I'm going to go towards 5. You ready? You know where you got to keep your eyes, right? Going towards the right, to the right, to the right. I'm following the graph, going towards the right. What is the y doing? It's staying put. The best prediction for the y value there is going to be that value. And so I would say that the limit of the function f of x as x goes to 5 from the left, that's a little minus, is equal to 2. 1, 2, 3, 4. From the left is equal to 2, from the right is equal to 4. We've got a right limit, we've got a left limit, but we don't have a, does not exist. We don't have a two-sided limit because they don't match. You get it? Alright, so we practiced a lot of the graphing. Let's practice some other methods for the two-sided ones. When you have a nice function like this, like sine x, the technical name for it is you have a continuous function, which we'll learn. That's coming up in like 1 or 2 lectures. When you have nice things like that, you could just plug it in, and you won't get an indeterminate form. You'll just get something like this: sine of pi over 2, and that's equal to 1, and you're done. The plug-in method, all the 4 methods that we had before, which we introduced in the most gentle way using only one-sided limits, all those 4 methods are now excellent tools to do the two-sided limits. Everything that we did before still works exactly the same way. You can also picture this if you have, just if it helps, picture it. Here's the graph of sine, and here's where you're going. You're going to pi over 2. Pi over 2 here, your ball would be going here. This is, and your best prediction here is 1. So, and there's no holes, there's no jumps. This is the ideal case where everything's nice. In the ideal case, all you do is to plug it in and you're done. See that? See why they pay me? Tangent is equal to, whoa, it's undefined. So much for the ideal case, huh? Tangent of pi over 2 is not a real number, and so, oh my goodness, so much for the plug-in method, so much for the ideal case. Now what? Well, now you got to go back to one of the other methods. The graphing idea still works. Here's pi over 2, and you've got to keep your eye on the ball here. Let's see, I got to move my x's. X's have to be getting closer and closer and closer to 2. So my x's are going here. My y's are going this way. What is the best prediction for the y value? The best prediction from the left is infinity. Now let's do from the right. X is going towards pi over 2 from the right. From the right, we do have a right limit. It's negative infinity. It's going all the way down. Now you can't see it, can you? Somebody should say something. Now can you see it? From the right, it's going down, negative infinity. From the left, it's going this way. They don't match. Therefore, we don't have a two-sided limit. We would say the limit does not exist. Okay. So the plug-in method works sometimes, but other times it doesn't. Let's try it again here. X is going towards 5. If you try the plug-in method, you get 0 over 0, which tells you this is less than ideal case. Well, it depends on your definition of ideal. If you like a challenge, then this is a little challenge. I like challenges. So then you got to try something else. The rewrite method. This is very, very famous type of problem. There's a recurring theme in all sorts of math textbooks, problems like this. I'll do that in just a second. You know what? I'm going to change my mind here. I'm going to go with engineer's method. Engineer's method. So I got to approach 5, but this time this is a slightly different take on the engineer's method. You got to go x is from the right. This would be the limit as x approaches 5 from the right, and then you got to do the limit as x approaches 5 from the left, and you got to do these numbers. So you got to go both ways, and you have to make sure that they match. If they don't match, if they go like this or like this, we don't have a two-sided limit. If it doesn't have a plus or minus, it's a two-sided limit, unless it's infinity, which you can only get there from one side, or negative infinity. So I do a little engineer stuff, and so from the right here, 76.51, observe the value, 75.15, 75.002. If you had to guess from the right, you would probably guess that it's going towards 75. Okay, that's from the right. Now from the left, you got 73, 74.8, 74.999999. If you had to guess from the right, you'd have to guess that it's probably going to 75. They match, we've got success, the limit is 75. Engineer's method. I told you, the Fantastic Four. Graphing, plug, and engineer's method, rewrite, it's all good. And we learn them in the easiest, most gentle way by introducing the limits at infinity first. That was the whole strategy to our approach. I want to try this problem again. That was so fun. We want to try it again. We want to practice our other skills, rewrite method. Let's try a little rewrite. So I was saying earlier that this is a famous type of polynomial. There's a famous factoring that goes along with it. The difference of cubes is factored more or less like that. In fact, there's generalizations of that. You can play that with any kind of difference like this. Difference of fourth powers. Notice the number of x's decreases. 3x's, 2x's, 1x, no x's. The number of y's increase. No y's, 1y, 2y's, 3y's. Pattern is always the same. You can play this game all day long. But anyways, that helps you factor this problem over here. So I'm going to do a little rewrite. This is like, I'm going to think about it as 5 to the third, so I can apply my thing here. If you have x to the third minus 5 to the third, that would be x minus 5 times x squared plus 5x plus 25. Yeah? So that's how I'm going to do the rewrite here. I'm going to play it like that. X minus 5 times x squared plus 5x plus 25. All that over x minus 5. And here's something nice. These ones cancel, and now you're left with x squared plus 5x plus 25. And I should have limit here, but that's not enough, large enough. So let's roll with that. So now I try the plug-in method. The plug-in method, so I'm plugging in x equals 5. So that will give me 5 squared plus 5 times 5 plus 25. And let me see if there's anything. By the way, when you cancel these, there's 1 there and there's a 1 left there. So there's a 1 on the bottom, there's a 1 there. I don't see anything controversial here. Everything's completely determined. I see 25 plus 25 plus 25. And that gives me 75. I told you. That's why they pay me. We had already done this problem, right, with the engineer's method. And so it's nice to do it a couple different ways. Let's try that again. X is going towards 3. Here you could use the conjugates idea. Famous. We talked about that before. Conjugates. You would multiply top and bottom by the square root of x plus 3, the square root of x plus 3. And if you did that, everything will turn out nicely. But you probably already know how to do that, or you can do that. I want to show you maybe a different idea. It's also famous, floating around. Of course, your first attempt would probably be to do the plug-in method, and if you try the plug-in method, you get 0 over 0, so that you know you got to do more work. We're going to go with the rewrite here, and it's a famous rewrite. It's a different one than the conjugate idea. You look at the bottom, not so much as x minus 3, but based on the top, you think, wait, maybe I could make this a difference of squares. Yeah, but it doesn't look like squares. I know, but you could make it look like squares. This could be the square root of x squared minus the square root of 3 squared. After all, if you take the square root of 3 and you square it, you get 3. If you take the square root of x and you square it, you get x. I told you. But now you've done something really nice. You've changed it to look like the difference of squares. So this is the square root of x minus the square root of 3 times the square root of x plus the square root of 3. And now you got something good. Now we're rolling. Now this becomes 1, that becomes 1, and that becomes just 1 over the square root of x plus the square root of 3. And now you try your plug-in method again. Plug-in method. So I'm plugging in x is going towards 3, so I get 1 over the square root of 3 plus the square root of 3, which is 1 over 2 times the square root of 3, which is why they pay me. Okay? Yeah. Wow. That was a lot of talking. You could also try the engineer's method on this one. Again, to do the engineer's method, you want to approach 3. You actually, I grade this out on purpose because it doesn't matter what happens at 3. Limits are not questions about what happens at 3. If it was question about what happens at 3, all we would do is plug it in and done with it. No. Because when you plug it in, you often get an indeterminate, so that's not what we do. We want to see where it goes outside of bounds, so to speak. So that's why I grade out the 3. The 3 doesn't matter. It matters what it's approaching to as I get close to 3. On either side, I plug these numbers. They're getting really close to 3 from the right and from the left. And then we compute them and say, well, okay, this is approaching 2.007, 0.28886, blah, blah, blah. You got to say that it's approximately approximately 0.2887, something like that. It's hard to say because after all, this is engineer's method. But it's got to be approximately that, and I would bet all my money on the idea that that number right there is probably the same as 1 over 2 times the square root of 3. Of course, we did it 2 different ways. Rewrite an engineer's method. Okay. So maybe a couple more plugins or rewrites. This one you get 0 over 0. Maybe we could do a little rewrite. A rewrite would be x minus 2 times x plus 2 on the top, x minus 2 times x minus 2 on the bottom. That cancels this. And then you try to plug in again. X is going towards 2. Whoa, x is going towards 2. I get a 4 over what? 4 over 0? What? My name is who? My name is what? 4 over 0. Yeah, so this should remind you of something like this. When I see this, you should be able to think about this. The limit as x goes towards 0, 4 over x. This is what it should remind you of. And that's a variation of 1 over x, which, remember, goes like this, and the limit doesn't exist. And so the limit doesn't exist. Or if you're not down with the analogy here, you could just do the graphing method, and you see at x equals 2. Let me see, the graph would probably look like. Try a little graphing on this one. The graph looks like this. This is x equals 2. And let me see, we're going to x is going towards 2. And so this is doesn't have a plus or a minus, so I got to go from both ways. So as I go to, I told you this is a variation of the 1 over x. It's a famous one. It does exactly the same thing. As you go this way, it goes towards infinity. As you go the other way, it goes towards negative infinity. And so the limits don't match. And so we can conclude that the limit does not exist. Now, a lot of times when you get good at it, you got to do like hundreds of these problems. But you could just look at this and know that that's a variation of the famous one, 1 over x. You don't have to go through all this. But of course, you can go through all this, because you got the fabulous 4 at your site. You can always use any of them. Okay. Similar there. I don't want to do that one. All right. I think that's good for today. Today was really important because we discussed. Let me tell you something. We had discussed, all the previous lectures had been about x is going towards negative infinity or x is going towards positive infinity. Today, for the first time, we got to practice what a left limit is, what a right limit is, and what a two-sided limit is. That's crucial. That's big. In fact, most books start off with this part right here. But yeah, if you understand the concepts here, we're in really good shape to understand a lot more things. Okay, I think we should call it a day. I think we should walk out. What do you guys think? Peace.